All right, so in the last one, we were talking about the different models of the atom, right? We said that J.J. Thomson had come up with this model of the atom originally, but then Rutherford said, no, it's got to be the nucleus is much smaller in the middle. But then he had the electrons randomly flying around the outside. And then Niels Bohr came along and he said, no, 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 the electrons are actually in definite orbits. Right? And we were looking at that model, the Bohr model of the atom had them in definite orbits. We were calling those orbits energy levels. And then finally we said that the current model today, the modern model of the atom, is what we would call the quantum mechanical model. And the difference between Bohr's model of the atom and the quantum mechanical model is subtle, but there is a difference. Right? It kind of goes like this. If you wanted to describe where something was, so its position, and how fast something was moving, its velocity, you could do so for any object pretty easily, as long as the object is sufficiently large. For example, if I wanted to know where you were right at this moment, right? If I could see you, I could tell you right now exactly where you are and how fast you're moving, right? If I could see you right now, I would have no problem in being able to tell where you are, right, and how fast you're moving. That wouldn't be very difficult. And I think you could do the same thing for me. If you could see me right now, right, you could tell where I am and how fast I'm moving. That's pretty easy. In fact, you could do that for a lot of objects. But it turns out that once you start measuring things like electrons that are really, really like the smallest things in the universe, measuring the position and the velocity of it actually becomes impossible. Like, I could tell where an electron is, but then I couldn't tell how fast it's moving. Or I could figure out how fast an electron is moving, but then I couldn't tell where it is. It's weird. You're thinking, well, that's weird. That doesn't happen with anything else. You're right, but at that scale, the rules are a little different. In fact, there is even evidence, actual scientific evidence, that shows that small particles like electrons can actually exist in multiple places at once. And you're thinking, that doesn't make any sense. That can't happen, right? Like, for instance, you can't be in two places at once. You can't be sitting at home and at school exactly at the same time. That doesn't work. And you're right. For larger objects, it doesn't work. But for really, really small particles like electrons, it turns out that that's a thing. In fact, there's a whole principle about it. It's called the Heisenberg uncertainty principle. Heisenberg was the one that determined this property of electrons. And it turns out that we are uncertain of exactly where electrons are at any one time. It's weird. You're thinking, well, why can't I just look at it? And you'd think you'd be able to, but you can't. That's a little joke. Hopefully you get it, right? Heisenberg uncertainty principle. Anyways, here's how it affects the model of the atom, okay? Since we don't know exactly where an electron is at any one time, all we can do is talk about the probability of where it will be. So instead of saying, like Niels Bohr said, he said, electrons exist in definite orbits. Well, we can't do that. All we can do is talk about the probability of where they are. And so we're going to change the name slightly. We're going to call them atomic orbitals. It's a slight name change. And really, it doesn't completely throw out the window the Bohr model. It just tweaks it a little bit. Let me show you how we're going to tweak it. We're still going to use this concept of energy levels, okay? Just like we were talking about before, these rings that go around the nucleus where the electrons are, we're going to still talk about energy levels. Technically, they have a name. They're called principal quantum numbers. But you know what? We're not going to call them that. We're going to call them energy levels, right? In fact, we're going to abbreviate them with the letter N for energy levels. And it turns out that there can be up to 7 of them in an atom. All right? There can be up to 7 energy levels where the electrons can exist. But we're not going to stop there. That's where Niels Bohr would have stopped. He'd be like, okay, there's energy levels and that's it. But it turns out there's more to it than that. The energy levels can be split up into energy sublevels. These sublevels have been given abbreviations, either the S sublevel or the P sublevel or the D sublevel or the F sublevel. Sometimes if you want to try to remember those letters, because they're sort of random and odd, some people will say, oh yeah, smart people don't forget, right? S, P, D, F. Those are going to become really important letters. No, they don't stand for anything else. Okay? They're just letters that were used to designate the sublevels. And then within each sublevel, there are the actual regions where the electrons are found, and those are called the atomic orbitals. Now, if you're trying to picture all of this in your brain, let me give you an analogy. I kind of think of this like a building. So imagine that an atom is like a building. And if you want to know where the electrons are in the building, right, kind of like people in a building, you're going to have to look at several things. First of all, buildings have floors. Like, for instance, the high school has 3 floors, right? So the floors are like the energy levels. But then on each floor, there are rooms, right? So each floor is split up into several rooms. Those are like the sublevels. And then within each room, there are desks or chairs where the people sit. Those are like the atomic orbitals. So again, if you imagine this, we've got floors that are then split into rooms, and the rooms have several places where people can sit. And so the electrons in an atom are found in these orbitals, which are in a sublevel of an energy level. So let's create sort of a map of what this would all look like. And the first thing that we have to do is, even though I'm never really going to ask you to draw anything like this, I do want you to see what they really look like. Here's what the sublevels look like. So an S sublevel is the simplest of sublevels. Again, I don't know if the S really stands for simplest, but it's good, it works. And it turns out that an S sublevel is spherical. Now, how do we know this? We know this only because of the mathematics behind all of this. There are very large, scary math equations that govern how electrons exist in an atom. We're not going to even approach those. But if you put those really big, scary math equations into a computer and you have it graph these math equations, these are the shapes that you get. So the S sublevel is this spherical shape. Now, I want you to imagine a sphere, like a basketball, okay? Imagine you have a basketball in your hand. If you take a basketball in your hand and you were to turn it on its side, would it look any different than it did before? No. What if you were to turn it another way, like away from you? Would it look any different now? No. Basketballs, or any spheres, look the same no matter which way you turn them. Since there is only one way to orient an S orbital or a sphere, then we say that it only has one way that electrons can go in it. So it has one orbital. So S sublevels have one orbital to them. A P sublevel, as you can see in these pictures, looks a little different. They look like bow ties or dumbbells, right? Where they have these two regions. Now, if you take a shape like this, it turns out that if you were to turn it this way, or this way, or this way, it looks different depending on the way you turn it. So there's 3 different ways you can orient a p sublevel. And so there are 3 different ways that electrons can exist in a p sublevel. So we say that it has 3 orbitals. A d, as you can see, starts to get even more complicated in the way it looks. There are 5 different ways you can orient a d sublevel. That means there's 5 different ways that electrons can exist inside of that sublevel. And so we say a d sublevel has 5 orbitals. And then an F starts to get really crazy. It's really complex. There are 7 different ways it can be oriented. Therefore, there are 7 orbitals in an F sublevel. Now, what's important out of all of this is not the shapes. Like I said, nobody's going to ask you to draw these or describe them in any way. Really, the only thing that's important about this is that you remember that there are 4 sublevels, S, P, D, F. And each of them has a certain number of orbitals that can exist. S's always have 1 orbital, P's always have 3, D's always have 5, F's always have 7. So once again, you need to remember S, P, D, F, 1, 3, 5, 7. Right? S, P, D, F, 1, 3, 5, 7. Can you remember that? It's really important. What we're doing here is we're building this map, right? We're building this map of where all of the electrons could be in an atom. All right, so let's lay all of this out. All the things that we just talked about, let's lay it all out. So the first thing we said is that they have floors to the building. We call those energy levels, right? How many energy levels did we say there could possibly be? We said 7, right? So let's make a chart so that we have 7 energy levels. So 7 rows on our chart here. And then we're going to split each of these energy levels up into sublevels, right? I said that energy levels then are split into sublevels, kind of like the floors in a building are split into rooms. Now, how many sublevels can fit into each of these energy levels depends on the size of the energy level. The first energy level, remember, is the energy level that's right next to the nucleus. If you can picture it, we have that ring around the nucleus, and that ring, since it's so close to the nucleus, is not very big. The first energy level is small. It doesn't have a lot of room. So if you have a really small floor in a building, how many rooms can you put in it? Probably not many. This one can only hold 1 sublevel, the simplest one, S. Now, when we get to the second energy level, it's a little bit bigger because it's a little further away from the nucleus, so it has room for more sublevels. So it has an S, but it also has a P. The third energy level is a little bit bigger than that, so it's got room for more sublevels. So it has an S, a P, and a D. The fourth is even bigger than that. So now it has room for an S, a P, a D, and an F. Now that's the most sublevels there can be, right? There's no other sublevels we talked about. So 5, 6, and 7, even though they get bigger each time, they don't have any more sublevels they could have. So they also have S, P, D, F. Now each sublevel then is going to have orbitals. We were just talking about this, right? Like we said, an S always has 1 orbital. A P always has 3 orbitals. A D always has 5 orbitals. An F always has 7 orbitals. So what I'm going to do over here is I'm going to list then all of the orbitals that exist. So we have an S. It turns out that it's on the first energy level, and to not get it confused with the S's on the other energy levels, I'm going to call it the 1s. So the 1s has 1 orbital in it, right? Because it's an S. S's always have 1 orbital in them. In the second energy level, I have an S and a P. So again, I'm going to label them so I don't get them confused with the other S's and P's that are out there. This is going to be called the 2s and the 2p. Now, a 2s is an S, and S's always have one orbital to them. But the 2p, that's a p sublevel. P sublevels have 3 orbitals to them. That would make a total, by the way, if you're keeping count here, that would make a total of 4 orbitals in the second energy level, right? In the third energy level, I have a 3s, I have a 3p, I have a 3d. The s has how many orbitals? 1. The p has how many orbitals? 3. The d has how many orbitals? 5. So I have a 3s with 1 orbital. I have a 3p with 3 orbitals. And I have a 3d with 5 orbitals. Are you with me? Keeping up with this? So, and you can see how the pattern is going, right? I think you could probably predict what's going to happen on the next one. You have the fourth energy level, which has an S, a P, a D, and an F. So we have a 4S, a 4P, a 4D, and a 4F. And we know S's have 1 orbital. We know P's have 3 orbitals. We know D's have 5 orbitals. And F has 7 orbitals. So 4s has 1 orbital, the 4p has 3 orbitals, the 4d would have 5 orbitals, the 4f would have 7 orbitals. And again, if you're keeping count, that's 1 plus 3 plus 5 plus 7. That's 16 orbitals, all in energy level number 4. Now, energy level number 5 has the same number of sublevels. You would just call them 5s, 5p, 5d, 5f. But they would have the same orbitals to them, right? It would be 1 orbital here, 3 here, 5 here, 7 here. Now, I don't know about you, but I don't want to write all that out again. So just basically say, oh yeah, it's the same as 4, except everything now would start with a 5. It would be 5s, 5p, 5d, 5f. 6 would be the same, 7 would be the same, except you'd call it 6s, 6p, 6df, 7s, 7p, 7d, 7f. Right, now, here's what I want you to do. After you get all of this written down, because this is all really important, after you get all of this written down, let's do just a quick little exercise. I want to figure out how many electrons can fit on each of these energy levels. Now, there's going to be a rule that we're going to learn here in a little bit. It'll probably be in the next lecture. And the rule is that each orbital can hold 2 electrons at max. Okay? Each orbital can hold 2 electrons. So, for instance, let me get a pen out here. For instance, this 1s has 1 orbital to it. We just said that an orbital can hold 2 electrons. So if this has 1 orbital that can hold 2 electrons, then how many electrons total can fit on the first energy level? Just 2, right? There are 2 electrons that can fit on the first energy level because it only has 1 orbital. But the second energy level has 1 plus 3, 4 orbitals. And if you can fit 2 electrons in each orbital, and you have 4 orbitals, that makes a total of, well, I don't know where that came from. That makes a total of 8 electrons. Let's see if we can get rid of that. Try that again. And 8, that's better. Has 8 electrons. The third energy level then, right, the third energy level would have 1 plus 3 plus 5, so that's 9 orbitals. So 9 times 2 means 18 electrons could fit on the third energy level. And then I want you to do the same thing. I want you to do it for the fourth energy level, the fifth, the sixth, and the seventh. I want you to figure out how many can fit on each of those levels. And then I want you to add them all up and tell me what's the total. I mean, rhetorically, you can't literally tell me. But pause this, do that, and then start it up again, and we'll talk about it. So you've done this, right? You figured out that this one has 16 orbitals, which makes 32 electrons possible. This one would be the same, 32. This one would be the same, 32. This one would be the same, 32. Now, what's the total? Well, 2 plus 8 is 10. Then we have 28. What is that? 60, 92, 124, 156. So that makes a total of 156 electrons. So, if we had an atom that had an electron in every single orbital of every single sublevel of every single energy level filled, it would have 156 electrons. Now, I'd also like you to get out a periodic table. It's going to be important. We're going to need it, so you might as well get it out now. If you have to pause and go find it and pull it up, you can do that. But I want you to go look on the periodic table, and I want you to tell me, what's the biggest atom on the periodic table? What's the biggest number of electrons that any atom on the entire periodic table would ever have? Go look that up, and then come back to this. Right. Did you do that? You saw that the biggest atom on the periodic table is what? Number 118? So that means the heaviest, biggest atom that we know of in the entire universe would have 118 electrons. So, do we ever have an atom that ever fills all of these orbitals? Not even close, right? This model that we're kind of building up here, this model can hold 156 electrons. But we're only going to use maybe up to 118. And that's only if I decided to be really mean and give you a really big one like that, which we probably won't do in here. So we're never going to be using all of this, even though all of this is possible, right? It's theoretically possible that an atom could have all of this available for electrons to be in. Now, there is an easier way, or I should say at least faster way, of coming up with how many electrons can fit on each energy level. And let me show you just a really quick shortcut here. If you want to figure out the number of electrons that can fit onto one energy level, you can actually use a really quick equation, and the equation is 2n squared. Right? Where n, remember n stands for energy level. So if you want to know how many electrons can fit in an energy level, you just plug the number of the energy level in for n. So for example, how many electrons can exist in the third energy level? So what would n be? N would be 3. So if you plug in 3 for n, that means you would take 2 times 3 squared. Now, don't forget your order of operations. You have to do the square first. So don't take 2 times 3 and then square it. You've got to do 3 squared first and then times 2. So 3 squared is 9. 9 times 2 is 18. So the third energy level can hold 18 electrons total. Now, we just did that, right? It's not that hard to do without this. This is just an optional extra way. Well, there's that extra line. I don't know why that's happening. There's an optional extra way of figuring this out. Do you have to use this? No. Can you simply do it like we did back on this other slide here? Can you do it like that? Sure. That's fine. So this right here is going to be super important, because what we're going to do going forward is we're going to start creating maps of where the electrons are in an atom. We're going to call these maps electron configurations. And in fact, I think they're kind of fun to do, and I always treat them kind of like a game. And so we're going to learn how to play this game in the next lecture, and we're going to be using all of these energy levels and sublevels and orbitals. So you need to have this information down before we can play this game.